to be your video lesson for 3-1, graphing polynomial functions. Since we aren't really using the graphing calculators in class a whole lot, I will be doing this lesson with the focus of using Desmos to complete your graphing. So there are a few things that may differ from how we might do this if we were looking at this in person. So we're not doing the explore and reason. You don't need to worry about completing that, but we are going to look at the essential question: how do the key features of a polynomial function help you sketch its graph? So in topic 2, we were talking about quadratic functions, and all the functions had a greatest exponent of 2. Now we're going to be looking at polynomial functions. So you may still have some polynomials that have exponents that are 2, but maybe you have some that have greatest exponents that are 3 or 5 or even 1, because linear functions are still polynomial functions. So the first thing we're going to look at is standard form. So standard form of a polynomial is going to show all the terms combined that are alike, and the terms have to be in descending order by degree. So whatever polynomial you have, you always want to list the highest exponent first, and then the next highest, and then the next highest, until you get the whole way down to the constant and you've eventually run out of terms. So our first example here asks, how can you write a polynomial in standard form? Use it to identify the leading coefficient, the degree, and the number of terms. So we have negative 4x plus 9 plus 2x cubed. Well, 2x cubed should go first because x cubed is the highest exponent. The negative 4x is going to go next because that's the next highest, and then the 9 goes at the end because that is the constant term. The leading coefficient is going to be 2 because 2 is what's multiplied by the x to the highest power. The degree is going to be the highest exponent. So the degree of this equation, this polynomial, it's not an equation because there's no equal sign. The degree is 3, and then the number of terms, there's 1, 2, 3 terms. And you can see here, we have all that information down here. So again, leading coefficient, it's your non-zero factor multiplied by the greatest power of x, so that's going to be your 2. The degree is the greatest exponent, which is 3, and this is called a trinomial because it has 3 terms. So now example 2, this is something we're just going to talk about, and we're going to look at the end behavior of polynomial functions. How do the signs of the leading coefficient and the degree affect the end behavior of the graph of a polynomial function? So your polynomial function is going to be a function whose rule is a polynomial. That means on the one side of the equal sign, you're going to have a polynomial. End behavior is going to describe what happens to the function as x approaches positive and negative infinity. So basically, positive infinity means you are going to be looking to the right on your graph. Negative infinity means what's happening when you look to the left on your graph. So what's the right end doing? Is it going up? Is it going down? What's the left end doing? Is it going up? Is it going down? Normally, I would give this information in a handout. However, you guys have your online textbook. You can snip that out from there. Or if you want to, you can pause this video and you can snip it out because we are going to look at both parts here. So these are the 2 ways that positive leading coefficient problems can end. And you can see odd degrees and even degrees have 2 different things going on. Odd degrees, whether that's degree 1, degree 3, degree 5, degree 7, if they have a positive leading coefficient with an odd degree, your left end is always going to be pointing down and your right end is always going to be pointing up. It doesn't matter how many turns or how many twists it has in between. End behavior means we're just looking at the left end and at the right end and stating what is going to happen. And you can see here odd positive, down, and then up. There is a proper way to write these. That's not something I'm planning on focusing on this year. It just has to do with you would write out an equation basically using some symbols instead of some words. But as long as you get the arrows in the correct way and you recognize what's going on and how that's always consistent, that's what I want to focus on. If you have an even degree that has a positive leading coefficient, it doesn't matter how many turns you got going on in the middle, both ends are going to be pointing upward. And you'll find with even degree, whether it's positive or negative at the beginning, the ends have to be going the same direction. whereas odd degrees go in opposite directions. Odd positive, left is down, right is up. Even positive, both ends are going to be up. Now for negative leading coefficients, that's reversed. Odd negatives, the left is up, the right is down, and for even negatives, both ends are going to be going down. So again, odd degree, you can kind of think about that as trailing negative x. So you're going to be decreasing over your entire graph. You start up and you end down. And then for negative even degrees, both ends are going to be pointing down. So now we're going to look at that and consider this polynomial function. And I'm actually going to pull in Desmos to help me with this, to help with the graphing. And I may get up to draw in the graph because it's a little bit difficult to draw with the mouse. So there may be a slight pause in the video where you won't be able to hear me as well while I get up to do this. So if we look at this polynomial, the highest degree is 4. So this is an even polynomial because 4 is an even number. The leading coefficient is negative, so this is a negative even, which means my end behavior is that both ends are going to be going down. So whenever I look at this graph, both ends of my graph are going to be pointing downward. I'm going to take a look at this on Desmos to make sure that that lines up with what I said. So again, desmos.com, and you can use your graphing calculator if you would like to. You would just turn it on, hit the y equals button, and you would type that equation into y equals and hit graph, and then you could use trace to do the same thing that we're going to do. So I'm going to hit graphing calculator here. I need to go back here and write down this equation so that I have it. Okay, so let's type this in. So we have y equals negative 0.5 x to the fourth. I just used the caret key for that. Normally there is a keyboard down here in the bottom, but because I have these drawing tools on here, I can't quite see that. Plus 3x squared plus 2. Okay, so you can see we have some points going on here, and I can actually go and click on those. So we have those peaks. That's not quite where I'm going to be drawing those because I don't really want the decimals here. I do want this point, and I want to get some other points on here. Let's see here if it'll let me click on some other ones. You can see here if I click and hold, there we go. So I have the point negative 2, 6, and I think I have the point over here of 2, 6. I'm sure that there's an easier way here to actually go through. So let's make a table. Oh, there we go. If you click on the table instead of the equation, then you can see what the points are here. So these are the things I'm actually going to copy onto my table on here. So let's see. We have negative 2, 6. So there's x and y. Negative 2, 6, negative 1, 4.5. 0, 2, 1, 4.5. Whoa. I'll try that one again. 4.5. And then 2 is going to also give me 6. We are not going to go further than that because you notice if I come out to 3, I'm like way down here at like negative 9. So that's going to be beyond what we actually need to graph there. Okay, so there are my points, -2, 6, -1, 4.5. Notice that -2, 6 is not actually the highest point. Remember, we did talk about how it goes up a little bit higher than that. So on the next page where I actually go through and graph, this is continued from before. I do want to focus on my turning points here. So I have 0, 2. I have 1, 4.5, and -1, 4.5. I have 2, 6, -2, 6, and it is going to go up a little bit higher from that. Actually, before I hit that point, you can see here it actually reaches this peak at -1.73 and then 1.73. So whenever I go and connect those, I am going to demonstrate that it is going to go up a little higher. And let's go through and connect those right now. So these are going to be connected. We're coming up a little bit higher here and then coming down. Those are going to be connected, coming up a little bit higher. That was a little bit too high. Let's try that side again. And then coming down. So that's going to be a good idea of what your graph actually looks like. Now to focus on turning points. Your turning points are going to be where your graph is going to change from increasing to decreasing or vice versa. So decreasing to increasing. Minimums are where your function has the least value over an interval. So this right here is one of your minimum values. Even though it's not the absolute lowest point, it is still the lowest within that region, which qualifies it as a minimum value. Maximum values, there's actually two of those. Those are those peaks up here. That's where you take on the greatest value. So not only are those two the greatest value over in that area, those are absolute maximums, not just relative, which means they are the highest points on the graph. It's never going to go higher than this. And remember our end behavior where we had both ends going down because this was a negative even function. Both of my arrows in this graph are pointing downward. So part B, how can you use the graph to estimate the average rate of change over the interval -2 to 0? So I'm going to go back here and I'm going to put a point up here at -2, and I know this isn't completely accurate because this comes up a little bit higher, and then a point at 0, and then we would connect these. So I'm going to go ahead and connect those with a line. So we're coming down through and passing through both of those points there. If I wanted to find the average rate of change, that's going to be the slope from the x value of -2 to the x value of 0. The y, it's the difference in the y's. So the average rate of change is the slope. The difference in the y's over the difference in the x's. So this y is 2. Let's just write out the points here. 0, 2 is going to be one of my points. The other point is -2, 6. So it's going to be 2 minus 6 over 0 minus -2. And again, this will turn into a +2. So we actually end up with -4 over 2. My average rate of change then is -2. So you're just finding the slope of that graph. This is something that I do want to talk about a little bit. We're not actually going to do a whole lot with this one, but I do want to go through and at least estimate x-intercepts and then turning points. And then we're going to talk about the end behavior and what we would have to happen, but we're not actually going to go through and sketch this graph. So your x-intercepts are the boundaries between positive and negative. And up here, you can see it's positive on these intervals and it's negative on this interval. This is basically doing the reverse of what we did in section 1-1 way back in topic 1. So if it stops being positive at -4 and then starts being negative, that starts going into the negatives at -4, -4 has to be one of your x-intercepts because that's the boundary between positive and negative. And then it stops being negative at -1 and starts being positive there. So -1 also has to be an x-intercept. And then it stops being positive again at 4 and picks up being negative there. So 4 is also going to be an x-intercept. So -4, -1, and 4 are all places where you have to have x-intercepts. Turning points are where you change from increasing to decreasing or decreasing to increasing. So if we're decreasing from -infinity to -2.67 and then we start to increase there, -2.67 is going to have to be one of the turning points, which is going to be a max or a min. And if we're decreasing and then starting to increase, that's actually going to be a minimum value. So then we're increasing until we get to 2, and then we jump to decreasing there. So 2 has to be another place where there is a turning point. When you go from increasing to decreasing, that is going to be a maximum. So your end behavior on your left end, and to find the end behavior, you really want to just consider the increasing and the decreasing. If I'm starting off decreasing on my function, then the end behavior to decrease, your left end is going to have to look like this, because from left to right, your graph is moving down. And then, so I'm going down, and then I'm going up, and then I'm going back down again. This 2 to infinity is also decreasing. So that also has to happen. So that's the information that you have. And then if you wanted to, you could go through and sketch the graph from this. You may see this appear as a bonus, but this will not appear as a regular question for our class. This is an application using the graph to figure out where your maxes and mins are. This is not one we're going to look at. I believe I do have the notes for this, so you can look over this in the PDF if you want to see how to complete this type of question. There is a concept summary on page 136 in your textbook, so that's something that I encourage you to look over as well. So I hope this was helpful. I know it wasn't as thorough as it might have been if we were here in person. However, there's still a lot of really great information here on polynomials and the different types of things that we're going to be looking at for them. So go back, rewatch the video, look over the parts that you're not sure of, the parts that are still confusing. And if you still have any questions, please make sure to reach out to me and ask.